This is the fifth in a series of videos correcting various claims made about the Islamic Golden Age. See the first video in this series for the context. This video addresses claims about the influence of the Islamic Golden Age on the development of Western science. You will notice that this video is very long. There's a lot of ground to cover and there are many details to consider in depth, but you might not find all of it particularly interesting, so please use the timestamps in the video description to skip anything you'd rather not hear about or would prefer to hear later. It is claimed that Western science and technology had completely stalled after the fall of the Roman Empire and were suddenly propelled forward as a result of the immense knowledge received from Muslim commentaries on Greek and Latin texts. This video clip from a Muslim apologist shows a typical example of how this claim is made.
But what they failed to recognize was that most of these manuscripts were translated from Arabic from the works of prominent Arab Muslim thinkers. This paved the way for European development and the creation of new scientific fields such as chemistry and algebra, with calculations that were the basis of Copernicus and Newton's discoveries.
In 1996, Professor Edward Grant noted that this was a common view within scholarship of his time, noting that even though scholars recognized that, quote, modern science emerged in Western Europe as a result of the Scientific Revolution, end quote, the same scholars also believed that, quote, the emergence of modern science in the 17th century owes little or nothing to the Middle Ages, end quote. His book, The Foundations of Modern Science in the Middle Ages, first published in 1996, was part of a new generation of scholarship which has now overturned the previous view. The claim that prominent Arab Muslim thinkers paved the way for the development of European science simply isn't true. As demonstrated in the fourth episode in this series, the works of the prominent Arab Muslim thinkers were not translated into Latin until the 12th century, by which time the Western recovery of Aristotle was already well underway, the Western revival of the Greek scientific tradition had already been taking place for at least 200 years, and groundbreaking progress had already been made independently of any influence from the Muslim world. Islamic commentators on Aristotle had the greatest potential to influence Western European science. However, Professor Edward Grant comments that, quote, over the centuries, the number of identifiable Islamic philosophers is relatively small, end quote. He identifies 5 as the most important: Al-Kindi, Al-Farabi, Ibn Sina, Ibn Bajjah, and Ibn Rushd. The 3 most famous and influential Arab Muslim philosophers were Ibn Sina, also known as Avicenna, Ibn Rushd, also known as Averroes, and Al-Ghazali, also known as Al-Ghazalis. Grant says that these 3, quote, had the greatest impact on Aristotelian natural philosophy in the West, end quote. However, their influence arrived quite late in the Western scientific tradition. Ibn Sina lived in Persia in the 11th century and wasn't translated into Latin until the end of the 12th century. Even then, Dr. Jules Janssens makes the point that only parts of Ibn Sina's philosophical and medical work were translated, with most of his work left untranslated until at least the 15th century. Janssens does acknowledge that even these small parts of Ibn Sina's work had, quote, a major impact on the scholastic thought of the 13th century and later on, end quote. However, the impact was largely in the realms of religion and philosophy rather than science. The second prominent Muslim philosopher, Ibn Rushd, lived in Spain in the 12th century. However, his work wasn't translated into Latin until the beginning of the 13th century. The third prominent Muslim philosopher, Al-Ghazali, lived in the 11th to 12th centuries. Although Al-Ghazali's works started being translated into Latin in the 12th century, he had a less direct influence than Ibn Sina and Ibn Rushd. Professor Edward Grant says that although Al-Ghazali had, quote, a significant impact on the West, end quote, this had little to do with his personal contributions to science and philosophy. Grant explains that Al-Ghazali's contribution was, ironically, in his criticism of the views of other Muslim philosophers, such as Al-Farabi and Ibn Sina, of which only Al-Farabi's commentary was translated into Latin. Consequently, the influence of Ibn Sina, Ibn Rushd, and Al-Ghazali on the development of Western science cannot be dated any earlier than the late 12th and early 13th centuries. By this point, scholars in the West were already developing concepts which would be instrumental in laying the foundation of the modern scientific method and would be used by the later architects of the scientific revolution. These key concepts included atomism, empiricism, experimentalism, and natural law theory. Although Muslim scholars had developed some of these concepts earlier, at least in a rudimentary form, European scholars not only arrived at them independently, but developed them further and much more systematically, which is why the scientific revolution took place in Europe rather than in the Muslim world. This will be discussed in detail later. So what was the contribution of the three most famous Muslim philosophers? Ibn Sina, known by Latin writers as Avicenna, made significant contributions to medicine, but was most well known as a philosopher. Professor Robert Winofsky of the Institute of Islamic Studies at McGill University says that after his writings became available in Latin at the end of the 12th century, Ibn Sina, quote, came to exert great influence on European scholastic thought, end quote. Ibn Sina was widely read and studied by philosophers and theologians. His thoughts on metaphysics and religion in particular influenced the famous 13th century Italian theologian Thomas Aquinas. Ibn Sina's book, The Canon of Medicine, an encyclopedia summarizing centuries of Greek, Roman, and Islamic medical thought, was promptly translated into Latin and was used as a textbook in Europe for hundreds of years. However, for all this, he did not make any significant scientific breakthroughs and was typically known in Western Europe as a philosopher and medical practitioner. His most well-known and discussed scientific contributions were his writings on atomism and the origin of the world. Ibn Sina argued against the classical Greek idea of atomism, that everything is made of substances which can be divided repeatedly into smaller parts to the point of a collection of final, indivisible parts. In contrast, although atomism was dismissed by early medieval Western scholars who were influenced by Aristotle's rejection of it, during the 13th and 14th centuries it was revived in the West by scholars such as Henry of Harclay, Gerard of Odo, William Crathorne, Walter Chatton, Nicolas Bonnet, John Wycliffe, and Nicholas of Outrecourt. As a result of their work, atomism became an important component in the scientific revolution of the 17th century. Similarly, Ibn Sina agreed with Aristotle that the universe was eternal and had no beginning. In contrast, the 6th century Christian philosopher John Philoponus had already comprehensively destroyed Aristotle's arguments, and the concept of the universe having a beginning was held among Christian scholars for centuries, finally being formally recognized in modern science in the 20th century. Ibn Sina made various contributions to physics and mathematics, but they were more in the way of minor refinements than revolutions, and it was his philosophy, theology, metaphysics, and medical knowledge which had the greatest influence on Western scholars. The work of Ibn Rushd had a similar reception in the West. Like Ibn Sina, he produced a great work on medicine, which became a standard text in Western Europe for centuries. Drs. Abdelghani Tabaki and Samir Amr write that Ibn Rushd's book on medicine was, quote, taught in Europe until the 18th century, end quote. However, unlike Ibn Sina, the philosophy of Ibn Rushd was strongly rejected by Western scholars. Dr. Joseph Kenny says that Ibn Rushd's philosophical writings were critiqued by Bonaventura, Albert the Great, and Thomas Aquinas. Al-Ghazali's views on the philosophy of nature had the least impact of all, and were completely rejected by scholars in the West. He is most well known for his work entitled Incoherence of the Philosophers. Historian Alinur Dahanani explains that in this work, Al-Ghazali attacked other Muslim philosophers as heretics for adopting Greek concepts, viewing them as incompatible with the Quran. Dahanani says Al-Ghazi believed that, quote, apart from medicine, the natural sciences have no utility, end quote. Al-Ghazali made an exception for mathematics and logic, which he believed were neutral. Al-Ghazali was particularly antagonistic to Ibn Sina and Al-Farabi, arguing against their view of causality. In Al-Ghazali's view, there is no such thing as natural law, and no necessary connection between any event and a subsequent event. This means it is not possible to determine causes by observing actions and their apparent results. For Al-Ghazali, actions are the result of direct action by Allah, a philosophical view called occasionalism. Actions and results appear to be causally connected because Allah is an orderly being whose actions therefore have the appearance of natural law. Frank Giffel, professor of Islamic studies at Yale University, says, quote, Al-Ghazali uses this argument in a radical sense, end quote. He goes on to characterize Al-Ghazali's arguments as, quote, the fact that we experience cotton as burning every time fire touches us informs us neither, 1, about any causal connection between the fire and the burning of the cotton, nor 2, whether fire is the only cause, end quote. This is completely opposed to the foundation of empirical science, which is based on the concept that when action A is consistently and repeatedly followed by result B, then it is at least rational to infer a causal relationship between the two. This causal relationship must be tested further, according to the well-known principle that correlation is not causation, but it is testable. For Al-Ghazali, there is never any necessary causal relationship at all, since the action of Allah is sufficient to explain the result. The cotton placed in the fire does not burn as a result of the interaction of the properties of cotton and fire, but because Allah has willed that the cotton should burn at the same time that it is placed in the fire. A person whose head has been removed does not die as a result of their head being removed. They die because Allah has willed that they die at the same time that their head has been removed. Entire books have been written on the awkward convolutions of Al-Ghazali's philosophy, and for the sake of brevity, this coverage must suffice. The extent to which Al-Ghazali was responsible for the decline of scientific study in the Muslim world is also much debated, though current scholarship rejects the previous view that Al-Ghazali's views were the dominant contributing factor. See the bibliography of this video for sources of more detailed academic commentary on Al-Ghazali and his legacy. The relevant point for the topic under discussion here is that Al-Ghazali's view of science was very obviously rejected by Western scholars and would have completely crippled scientific development in Europe if it had been taken seriously. Al-Ghazali, despite his fame, did not contribute to the successful rise of science in the West. Ironically, by the time these greatest of the Muslim philosophers were finally reaching Western scholars, the study of Greek philosophy in the Islamic Golden Age itself was virtually dead. Professor David Deming says, quote, in the 11th century AD, Hellenistic studies in the Islamic civilization were on the wane, and by the end of the 12th century AD, they were essentially extinct, end quote. So Ibn Sina, Ibn Rushd, and Al-Ghazali, the greatest of the Muslim world's philosophers, did not actually start influencing Western scholars until at least the 12th century. Of these three, Ibn Sina's influence on Western scholars was almost exclusively in the fields of philosophy and religion, rather than science. Ibn Rushd's medical knowledge was widely accepted and revered in the West, but his philosophy was robustly opposed, and Al-Ghazali's original ideas were totally rejected. Why is it important to focus on these three philosophers in particular? Because we're testing the claim of this Muslim apologetic video, which states Ibn Rushd was, quote, the Muslim philosopher who paved the way to the European Renaissance, end quote. This next section will be lengthy, and you might consider it to be an unnecessary distraction from the main subject of this video, so if you think it's getting a bit slow or irritating, just use the timestamps in the video description to skip forward until you're where you'd rather be. It has now been demonstrated that the works of Ibn Sina, Ibn Rushd, and Al-Ghazali certainly did not pave the way for the development of European science, even despite the medical and philosophical contributions of Ibn Sina and Ibn Rushd. However, these were by no means the only Muslim writers whose works were read and studied in Western Europe. From the 11th century to the 13th century, Arabic works from many Muslim writers were translated into Latin by men such as Solomon ben Gabriel, Raymond de Sauvetat, Constantine the African, John of Seville, Plato of Tivoli, Gerard of Cremona, Gundisalvus, Michael Scott, Roger Bacon, Robert Grosseteste, Whittelow, Robert the Englishman, and Arnold of Villanova. Ironically, some of these lesser-known works contributed more to Western science than the works of the three greatest Muslim philosophers we've already looked at. Professor Charles Burnett of the History of Islamic Influences at the Warburg Institute comments that intellectual exchanges between Western and Muslim worlds, including European, Arabic, Persian, and Jewish scholars, reached a high point during the 13th century. He notes that, quote, the end of the 13th century and beginning of the 14th witnessed the translations of great summae on philosophy, astrology, and medicine, end quote. However, he also notes that by the end of the 14th century, quote, The major works on mathematics, medicine, and philosophy had been translated. No new translations of great importance from Arabic appeared until the Renaissance." End quote. After 2 centuries, the age of Muslim contributions to European scholarship was virtually over. There were a couple of reasons for this decline in intellectual influence from the Muslim world. One was that by this time the Islamic Golden Age itself was slowing down. The reasons for the decline and fall of the Islamic Golden Age are complex, and the issue has been debated for years in mainstream scholarship. But the Mongol invasion by Hulagu Khan in 1258, which captured Baghdad and destroyed the House of Wisdom, was certainly a contributing factor. This devastating event crippled the Abbasid Empire, whose rulers retreated to Egypt, and it reduced the great libraries of Baghdad to ashes, depopulating the city, which took decades to recover. Subsequent to its capture, Baghdad eventually became an important trading point under Mongol rule, but was no longer the leading centre of intellectual activity which it had been. Another reason for the reduced influence of Muslim scholars on the West was the fact that Western scholars themselves were losing interest in Arabic works as a result of the full-scale recovery of the Western intellectual tradition preserved in the Greek classical texts. Professor Charles Burnett observes that from the middle of the 13th century, around the same time that the Muslim world was devastated by the Mongol invasion, Western scholars were turning their attention to, quote, translating directly from the Greek, end quote. He explains that the works of men such as Roger Bacon, Robert Grosseteste, William of Moerbeke, and Nicholas of Reggio not only produced new Latin translations of Greek texts already existing in the West, but also replaced any earlier translations from Arabic until the extant Greek classical heritage had been virtually entirely recovered. At this point, there was no need for Arabic translations, and interest in Arabic commentaries likewise declined, though some of these commentaries remained influential for centuries to come. However, despite the decline of direct interaction between Western and Muslim scholars from the end of the 13th century onwards, writings by Muslims which had already been translated continued to have both a direct and indirect influence on the development of science in Europe. In order to address accurately the contribution of the Islamic Golden Age to the development of European science, it is necessary to establish some guidelines for assessing the historical sources. In the history of science, it can be extremely difficult to identify the original source of a concept, to determine who influenced who, and to determine the extent of any one individual or group's contribution to the overall development of science. This is particularly the case when multiple individuals were working on the same problems during the same era. In this case, the difficulty is compounded by the fact that the events being examined took place between 800 and 1200 years ago. Professor Peter Dronke, a leading scholar in medieval Latin literature, issues a caution about the difficulty of detecting Muslim influences on Western intellectual works, writing, quote, "We should avoid overestimating the importance of these Arabic influences, or, since we are looking for them and expecting to find them, seeing them where they do not exist." End quote. He notes that we cannot rely on the mere presence of specific terms and phrases, since it is impossible to determine direct or indirect influence on this basis alone. As an example, he points out that Bernard Silvestris uses the phrase elementas elematum, which he could have borrowed from the Latin translation of the work of Muslim scholar Abu Mashar, but that the same phrase appears even earlier in the writings of the Frankish scholar William of Conches. So did Bernard borrow the phrase from Abu Mashar or William of Conches or somewhere else? Or did Bernard arrive at the phrase independently? Without additional information to provide a broader context, such as Bernard's direct citation of an earlier author, or a more obvious pattern in Bernard's work of dependence on another writer, it is not possible to tell. As another example, the Christian scholar John Philoponus, who lived in Alexandria in Egypt during the 6th century, came to various important conclusions concerning physics, in particular with regard to motion and force, developing a theory of impetus. In the 14th century, the French scholar Jean Buridan wrote on the same subject, coming to an extremely similar theory of impetus. However, it would be a mistake to simply assume that Buridan had access to and was influenced by the writings of John Philoponus. Physicist Peter Hodgson writes, quote, "There has been some speculation about whether the ideas of Philoponus were known to Buridan, but nothing seems to be established definitely on this question." End quote. So what was the source of Buridan's conclusions on impetus? Buridan's own work cites previous commentary on impetus by a scholar of the Islamic Golden Age, Abu Barakat, a Jew of the 12th century, who drew conclusions similar to those of Philoponus. It is therefore reasonable to conclude that Buridan was influenced by Abu Barakat. However, Abu Barakat himself was modifying the work of another scholar of the Islamic Golden Age, the Muslim Ibn Sina, who wrote a century earlier. Was Ibn Sina therefore the ultimate source of Buridan's theory of impetus? At this point, it would seem fairly obvious to answer yes. But the issue is complicated even further by the fact that Ibn Sina explicitly reveals that he is building on the work of a much earlier scholar, none other than the 6th century Christian John Philoponus. So who inspired Buridan's work on impetus? Was it Abu Barakat, whose work was used by Buridan, Ibn Sina, whose work was used by Abu Barakat, or Philoponus, whose work was used by Ibn Sina? The best way to assess this is to determine whether Buridan's own views were the closest to the views of Abu Barakat, Ibn Sina, or Philoponus. Even if this does not demonstrate direct influence from a specific scholar on Buridan, at least it shows that he rejected the views of the other scholars. In this case, it is clear that Buridan's conclusions on impetus were the closest to those of John Philoponus, and that even though Buridan had direct access to the views of Abu Barakat and indirect access to the views of Ibn Sina, he rejected both their models of impetus. Although it is not clear that he was influenced by Philoponus, it is clear that he did not accept the views of the earlier Jewish and Muslim scholars to whom he had been exposed. The issue of who was influenced by whom, therefore, is not always demonstrable even when a writer identifies clearly the sources with which they are interacting. Another problem is identifying the extent to which a writer contributed to a concept which was eventually foundational in the scientific revolution. The complexities of such questions are discussed endlessly in academia and are well beyond the scope of this video. Instead, we can focus on a much narrower issue, which is testing the claim made by this Muslim apologist video.
But what they failed to recognize was that most of these manuscripts were translated from Arabic from the works of prominent Arab Muslim thinkers. This paved the way for European development and the creation of new scientific fields such as chemistry and algebra, with calculations that were the basis of Copernicus and Newton's discoveries.
So the claim is that Arabic texts written by prominent Arab Muslim thinkers paved the way for the development of European science by creating new scientific fields such as chemistry and algebra, with calculations that were the basis of Copernicus and Newton's discoveries. The video unfortunately doesn't provide any evidence for these claims or any examples of exactly what is meant, so we'll need to do the research ourselves. Let's start with chemistry.
Jabir bin Hayyan, the father of modern chemistry. He invented the idea of a laboratory, and he says the first essential in chemistry is that thou should perform practical work and conduct experiments.
This will be another long and detailed section, so again, feel free to use the timestamps in the video description to skip this if you prefer. Prior to the scientific revolution, modern chemistry as we know it did not exist. Instead, there was a discipline called alchemy, a combination of two Arabic words, and the word from which the English word chemistry derives. The most significant difference between alchemy and modern chemistry is that alchemy was based on a completely inaccurate understanding of matter. This misunderstanding was so crippling that modern chemistry emerged comparatively late in the scientific revolution, in the 18th century, well behind significant advances in other fields such as mathematics, optics, astronomy, and physics. Even in the late 17th century, famous scientists such as Robert Boyle and Isaac Newton were still practicing alchemy with a firm belief in the philosopher's stone, a mysterious compound which was believed to transmute base metals into higher metals, such as turning lead into gold. Professor Lawrence Principe of the Department of Chemistry at Johns Hopkins University describes the origins of alchemy in the Greco-Egyptian period of the 3rd century. He describes the first phase of alchemy as taking place from the 3rd to the 9th century, during which the Greeks and later Byzantines, quote, set alchemy's foundations and established many features that would characterize it for the remainder of its life, end quote. Principe explains that it was in the 8th century that Arabs of the Islamic Golden Age, quote, sought out this Greek heritage and then massively augmented it with fundamental theoretical frameworks and a wealth of practical knowledge and techniques, end quote. So, contrary to Muslim apologist claims, it can't be said that the Islamic Golden Age created chemistry as a new scientific field, since chemistry didn't exist before the 18th century. And it can't be said that the Islamic Golden Age created alchemy as a new scientific field, since alchemy already existed from the 3rd century to the 9th century and was actually learned by Muslim scholars from Greek and Byzantine writings. However, it is true that alchemy was brought to Western Europe through Arabic texts. Principe writes, quote, "Alchemy, we are told, arrived in Latin Europe on a Friday, the 11th of February, 1144, end quote, explaining that it was on this day that the English monk Robert of Chester translated an Arabic work on alchemy into Latin. Principe mentions that Robert decided to translate this text because, in Robert's own words, quote, "Our Latin world does not yet know what alchemy is and what its composition is," end quote. The history of alchemy in Western Europe, therefore, starts with knowledge learned from Arab scholars in the Muslim world. Consequently, Principe says, quote, "Thus, when alchemy arrived in medieval Europe, it came as an Arabic science, its lineage signalled by the Arabic definite article al affixed to the word itself," end quote. He adds, quote, "It was thereafter in Europe that alchemy saw its greatest flowering and largest following," end quote. By the time alchemy arrived in Western Europe in the 12th century, Arabic scholars in the Muslim world had already been studying it for nearly 400 years. A paper entitled The Arab Contribution to the Development of Chemistry in Europe, written by Dr. Maria Jardim and Dr. Maria Maya of the University of Lisbon, together with Professor Joseph Legowski of the University of Texas, describes the contributions of the Islamic Golden Age to the science of chemistry. Speaking specifically of the achievements of Arabic scholars between the 13th and 15th centuries, they write, quote, "Their innovation in chemistry was the result of a remarkable culture of the practice of experimental work, leading to the design and use of instruments and techniques including chemical operations like solidification, fusion, calcination, distillation, and sublimation," end quote. The most famous and influential alchemist of the Muslim world was Jabir ibn Hayyan. Muslim scholars credited him with a breathtaking 3,000 works on the subject, though most of them consisted of only a few pages. However, modern historians have determined that records of Ibn Hayyan are wildly inaccurate, and that the body of work attributed to him was in fact written by many different people over a century. Principe points out that the accomplished Arabist Paul Krauss concluded, quote, that many authors were responsible for Jabir's 3,000 works, and that these had been composed over the course of a century, end quote. Nevertheless, the collection of alchemical texts attributed to Jabir ibn Hayyan, known as the Jabirian Corpus, does contain an impressive number of innovations. These include around 20 different pieces of equipment for chemical research, many of which have become standard items in modern laboratories, descriptions of chemical operations such as distillation and crystallization, the production of various acids, an extensive classification scheme for chemical elements, and instructions for the derivation of inorganic compounds from organic substances. Another significant alchemist in the Muslim world was Al-Razi. Principe writes that not only was he, quote, one of the most famous physicians and alchemical writers in the Islamic world, end quote, but also adds, quote, his works remained authoritative texts in Europe until the 1600s, end quote. It must be remembered that Al-Razi was not a Muslim. He was actually an anti-Muslim skeptic who wrote various criticisms of Islam. Nevertheless, his contributions are still part of the Islamic Golden Age and must be considered when assessing the impact of that era on the development of modern chemistry. Two other scholars in the Muslim world made useful contributions, Al-Kindi and Ibn Sina. Although neither of them were practitioners of alchemy, Principe writes that both of them argued against the traditional alchemic teaching of chrysopoeia, the false belief that base metals could be transmuted into gold through a complicated chemical process. Unfortunately, this useful criticism was not influential in the Muslim world, whose alchemists remained convinced that chrysopoeia was a fact. However, when Ibn Sina's work was translated into Latin, his arguments against chrysopoeia had far more effect in Western Europe. Principe writes that, quote, Ibn Sina's denial of the possibility of true transmutation turned out to be extremely influential, for this section of his book of the remedy would later be translated into Latin and widely circulated in Europe, end quote. Having considered the most significant alchemists and alchemical works in the Islamic Golden Age, it is now necessary to assess the contributions they made to the emergence of modern chemistry. The paper cited previously by Jardin, Meyer and Al-Ghazali makes the very strong claim that, quote, without this extraordinary development, it would have been very difficult for the scientific revolution of the 17th century, followed by Lavoisier's chemical revolution in the 18th century, to happen at that time in Europe, end quote. This is a claim that the alchemical work of the Islamic Golden Age was directly responsible for both the scientific revolution of the 17th century and the later chemical revolution of the 18th century. But to what extent is this true? It is certainly a fact that Western European scholars considered the Arabs to be not only the originators but also the masters of alchemy. For a century, Arabic works on alchemy were sought out, translated, and distributed throughout Europe. Almost the entire Western alchemical vocabulary was borrowed directly from Arabic, as Arabic alchemical terms were adopted by Western scholars directly without translation. The word alchemy itself from the Arabic alchemia, alkaline from the Arabic alkali, borax from the Arabic burak, azurite from the Arabic lazawad, sodium from the Arabic suwad, riogar, which is ruby sulfur, from the Arabic ra al-gar, aniline from the Arabic anil, natron from the Arabic natrun, alcohol from the Arabic alcohol, elixir from the Arabic al-iksir, alembic from the Arabic al-inbik, and many others. Arab alchemists were so greatly respected and admired that some Western scholars even wrote their own works on alchemy under false Arabic names in order to give them an air of authority which even a Latin name could not command. Additionally, unlike other developing sciences which were virtually entirely mathematical, such as optics, astronomy, and physics, alchemy provided an almost unique opportunity to encourage practical experimentalism, since it depended on the direct application of knowledge through repeated physical procedures which provided quantifiable feedback. When an alchemical procedure was followed and was perceived to have failed, the alchemist would examine carefully their equipment, chemicals, and the written source of the instructions they were following in order to determine what went wrong. They would then modify the procedure as deemed necessary and repeat it in search of success. This led to observational experience taking precedence over theory and intuition, and encouraged the process of experimentation as a reliable method of determining facts. Although this was not yet the scientific method, it was certainly the encouragement of a practice which would eventually become one of the foundations of modern science. This is of particular importance since it has long been considered that the medieval era was a time when experimental methodology did not exist. In contrast, William Newman, professor of history and philosophy of science at Indiana University, writes, quote, "The role of medieval alchemy in nurturing an incipient experimentalism points to the need to revise the traditional identification of medieval science with a supposedly non-experimental, academic, natural philosophy." End quote. So the alchemists of the Muslim world must be credited with introducing alchemy to the Western world, developing a specific alchemical vocabulary, inventing numerous implements and procedures for alchemical investigation, and systematizing alchemy as a proto-science. Without these contributions, it is uncertain how modern chemistry would have ever developed in Western Europe. In Eastern Europe, the Byzantines had preserved the Greek alchemical tradition, but they never developed it to the extent that the Arabs did in the Muslim world. The chemical revolution of the 18th century was indisputably built on the foundations of these contributions from the Islamic Golden Age. However, does this support the claim of Jardin, Meyer and Al-Ghazali? They write, quote, "Without this extraordinary development, it would have been very difficult for the scientific revolution of the 17th century, followed by Lavoisier's chemical revolution in the 18th century, to happen at that time in Europe." End quote. This is a considerable step beyond the observation that modern chemistry has roots in Arabic alchemy. It is an explicit claim that Arabic alchemy was directly responsible for the scientific revolution and was therefore also directly responsible for the later chemical revolution. This is a much more difficult claim to support. It is certainly demonstrable that Arabic alchemy led to Western alchemy, and even that Arabic alchemy was at the root of Western chemistry. However, crediting Arabic alchemists with the scientific revolution is quite a different issue. This next section will be quite lengthy and involved, So, as before, if you're finding it a distraction or perhaps just not very interesting, use the timestamps in the video description to skip forward to wherever you would rather be. It is certainly true that the 18th century chemical revolution was, at least in part, a product of the 17th century scientific revolution. But to what extent was the Arabic alchemy directly responsible for the scientific revolution? If these seem like pedantic distinctions to make, let's move further back in history. It is a fact that Arabic alchemy was the product of borrowing from earlier Greek and Egyptian sources. If the Arabs had now discovered and borrowed the alchemy of the Greeks and Egyptians, it is difficult to imagine how Arabic alchemy could have ever come about. But should we then credit Greek alchemy with the 17th century scientific revolution, or the 18th century chemical revolution? No, because those Greek alchemists made no discoveries which contributed to the groundbreaking ideas of either of those revolutions. Can we credit Greek alchemy with the new discoveries of Arabic alchemy during the Islamic Golden Age? No, because the Greek alchemists made no contributions to the groundbreaking ideas of Arabic alchemy. It may help to imagine the progress of alchemy as a series of steps rather than a continuously rising line. Greek alchemists made certain advances before reaching a plateau. Scholars of the Islamic Golden Age started from the foundation laid by the Greeks, but made their own advances for which the Greeks themselves were not responsible. In turn, Western scholars in alchemy started from the foundation laid by the Arabs, but made their own advances for which the Arabs themselves were not responsible. At each point that the subsequent culture reached a new stage of development, it was the product of a break with the ideas of the previous culture, not a complete continuity with them. Arabic alchemists advanced further than the Greeks because they departed from the ideas of the Greek alchemists, and Western alchemists advanced further than the Arabs because they departed from the ideas of the Arab alchemists. If we present this progress as a continually ascending line, it would look like advancement at each point was simply inevitable. We could say that given enough time, the Arabs would have arrived at the chemical revolution themselves. Or we could say that, given enough time, the Greeks would have arrived at the chemical revolution themselves. However, the historical facts strongly suggest otherwise. The Greeks reached a plateau, and there is no evidence that it was inevitable that they would progress further, given enough time. The Arabs likewise reached a plateau, and there is no evidence that it was inevitable that they would progress further, given enough time. The medieval Western alchemists reached a plateau, and although we know they did progress further to the chemical revolution, there is no evidence that this was inevitable. In fact, it seems that this progress could not have happened without the scientific revolution, and that revolution itself was far from inevitable. Returning to the Muslim apologist claim, if it is true that Arabic alchemy did make the Western scientific revolution possible, then what did it contribute in order to achieve this? Not maths or physics, because Arabic alchemists made no progress in these fields. Not astronomy or optics, because Arabic alchemists made no progress in these fields. Not atomism, empiricism, or natural law theory, because Arabic alchemists made no progress in these fields either. The most that can be said for Arabic alchemists with regard to the scientific revolution is their encouragement of experimentalism, which was a critical element in the scientific method. However, experimentalism already existed within Western scientific research by the time Arabic alchemy was being transferred to the West, so this was not a unique Arabic contribution. The history of the development of the scientific method will be addressed in a later video. What can be said for the Arabic alchemists is that they transferred to the West a modified version of Greek alchemy, which was in some ways much more systematically developed and advanced. However, at its core, Arabic alchemy still maintained a completely inaccurate understanding of matter, derived from the elemental theory of Aristotle. Every material was considered to be made of 4 elements: earth, water, air, and fire. Modern chemistry could not arise until this fundamental error was corrected, and alchemists of the Muslim world never corrected it. In fact, Western alchemists of the late medieval era and Renaissance never corrected it either. It took the scientific revolution of the 17th century to finally overcome this critical roadblock to the development of modern chemistry, starting with the work of Jan-Baptiste van Helmont and Jean Rey in the 16th century, and Robert Boyle in the 17th century, and culminating in the work of Antoine Lavoisier in the 18th century. This may seem like an overly lengthy justification for denying that the scientific revolution and chemical revolution were the product of discoveries made by Arabic alchemists, so at this point let's return to the history and examine an important break which took place between Arabic and Western alchemy in order to demonstrate the evidential basis for the claim being made. As seen previously, Western scholars were immediately fascinated by alchemy as soon as they came into contact with it in the early 12th century, and adopted it virtually wholesale from the Arabs, along with a system of thinking about the material world which had been devised by Arab alchemists. 100 years later, in the early 13th century, Western borrowing from Arabic alchemy had reached its peak. At this point, the scientific revolution was still 400 years in the future, and the chemical revolution another 100 years further away. If the Muslim alchemists made contributions which enabled the scientific revolution, why did it take 400 years for that revolution to take place? The simple answer is that the Muslim alchemists did not make or pass on the critical discoveries which would contribute to the scientific revolution. During the 13th century, Western alchemy started to break with the Arabic tradition. Western scholars were now writing their own works on alchemy and were no longer interested in simply borrowing and systematizing earlier Arab findings. Principe says it was at this time that, quote, the translation of Arabic alchemical works dwindled to a trickle, end quote, adding, quote, by that time, Latin authors had begun writing their own books on alchemia, end quote. As mentioned previously, it was around this time that the Western recovery of Aristotle and the rest of the classical Greek canon was virtually completed, and European scholars were turning their attention from Arabic sources to the newly available Greek sources, which, in many cases, they considered to be superior. The influence of Arabic alchemy on Western science started to decline significantly at this point. Western scholars used the new ideas they found in Aristotle and other works and challenged both their previous alchemical assumptions and the alchemical knowledge they had learned from the Arabs. Applying a more rigorous Aristotelian approach, Western scholars started to break with the Arabic alchemical tradition. During the 13th century, Paul of Taranto, an Italian Franciscan monk, started a new line of research which led Western alchemists away from the Arabic legacy. Principe says, quote, undeniably, Paul's works display the results of extensive practical testing and experimentation, and a level of rigor and theoretical synthesis rarely found in Arabic sources, end quote. He suggests this may be due to, quote, the Christian West's taking more seriously Aristotle's charge to discover the true natural causes of things than was widely the case in the Islamic world, end quote. Paul's new approach soon dominated the Western alchemical tradition. Principe writes that Paul's great work on alchemy, the Summa Perfectionis, quote, became one of the most influential alchemical books of the Middle Ages and remained an authoritative text until the 17th century, end quote. More importantly, Paul combined an idea from Arabic alchemy with various suggestions of Aristotle to develop a theory of material compounds being made up of very small particles. Although this was not yet the fully fledged atomism of the scientific revolution, it was a significant step towards it. Principe notes that Paul's proto-atomism was only followed by some subsequent Western alchemists, but that, quote, his theory would persist and develop as one important thread among the various theoretical traditions of European alchemy, end quote. This theory was not developed further until the 17th century. However, it became important not only to the scientific revolution, but even more so to the later chemical revolution. So this was one alchemical theory which did have an impact on the scientific revolution, but it did not come from the Arabs. It came from Western scholars who had departed from the Muslim alchemical tradition. 300 years after Paul of Taranto had broken away from the Muslim alchemical legacy, Western alchemists had surpassed their Arabic teachers. Principe says, quote, by the start of the 16th century, Latin alchemy had developed in many ways beyond the Arabic alchemy Europe had acquired more than 3 centuries earlier. It should be noted that Western alchemy itself did not contribute directly to the scientific revolution. It did have an influence on the chemical revolution, but only because it broke with and developed further than the achievements and theories of Muslim alchemy. Contrary to the claims of Muslim apologists, therefore, Arabic alchemy did not contribute to either the scientific revolution or the later chemical revolution. Now let's examine the claims that translations from Arabic were responsible for calculations that were the basis of Copernicus and Newton's discoveries. We'll start with the general Muslim contribution to mathematics, which was considerable. The most widely known contribution was, of course, the system of decimal numerals, including 0, commonly referred to today as Arabic numerals, though the Arabs actually borrowed them from the Hindus. Although these numerals were not invented by Muslims, it was through Arabic writings that this system found its way to Europe. Consequently, sociologist Toby Huff says, quote, "The Arabic borrowing of the Hindu numeral system must be awarded high recognition," end quote. Additionally, Muslim scholars of the Middle Ages generally had better access to Greek works on mathematics than their European counterparts, at least until later centuries. Muslim scholars had early access to the writings of Euclid of Alexandria, who was indisputably the greatest Greek mathematician of the pre-Christian era and is regarded as the founder of geometry. During the 12th century, European scholars were well aware of how far ahead the Muslims were in this field. Charles Burnett, professor of the history of Islamic influences in Europe of the Warburg Institute, says, quote, "Stephen the philosopher lamented the poor knowledge of geometry among the Latins, and John of Salisbury reckoned that the only place where the study flourished was in Islamic Spain," end quote. Likewise, sociologist Toby Huff writes, quote, "Just how far advanced the Arabs were in the field of mathematics has recently been stressed by Rushdie Rashed," end quote. He adds, quote, "Arabic mathematicians in the 11th and 12th centuries achieved mathematical innovations that were not accomplished by Europeans until the 15th and 16th centuries," end quote. The most well-known Arabic contribution in mathematics is a specific form of algebra. Algebraic problems had been solved in various ways in earlier centuries. Euclid used geometry in a system known as geometric algebra rather than the symbolic algebra used today. In the 4th century, Diophantus of Alexandria used a form of symbols to represent unknown numbers in a system known as syncopated algebra. However, neither of these systems were the algebra of the Muslim world, which developed into modern algebra. In the 9th century, Persian polymath Muhammad ibn Musa al-Khwarizmi wrote Al-Jabr wal-Muqabala, or the compendious book on calculation by completion and balancing. The English word algebra itself comes from a Latinization of the first word in the book's title. This was a revolutionary work presenting a new form of algebra which was different to both Euclid's geometrical method and the syncopated system of Diophantus. Al-Khwarizmi is therefore rightly credited with the foundation of modern algebra. In 1145, this work was translated into Latin by Robert of Chester and remained widely used in Europe as a standard textbook for the next 500 years. The Muslim apologist video we saw previously cites Muslim creation of, quote, "new scientific fields such as chemistry and algebra, with calculations that were the basis of Copernicus and Newton's discoveries," end quote. So we should find evidence that algebra was instrumental in the achievements of Copernicus and Newton. However, we do not. This is particularly curious given that it was during Copernicus' era that Al-Khwarizmi's algebra was being refined. Al-Khwarizmi's original system was rhetorical algebra, meaning every calculation was laboriously written in sentences as words, including every number. It did not use a combination of numerals and symbols as modern algebra does. The change from rhetorical to symbolic algebra was made by European scholars in the 16th century. Historian of science Professor Carl Boyer wrote, quote, "The conversion of Arabic algebra into a symbolic discipline was one of the chief contributions of the contemporaries of Copernicus to mathematics," end quote. However, despite the fact that algebra was being refined by his contemporaries, Copernicus found no use for it in his own work. His own revolutionary book, De Revolutionibus, used the same mathematics as the Greeks, including geometric algebra and basic trigonometry. He used none of the mathematical innovations of the Muslim world. With regard to Newton, the case for his dependence on the mathematics of earlier Muslim scholars is even less credible. Like Copernicus, in his work on physics, motion, and the planets, Newton deliberately did not use algebra, despite having been taught it at school. Instead, he used Euclidean geometry, which he believed was more appropriate. In fact, Newton was so devoted to geometry that he constantly referred to Euclid's original works when writing his own great work on mathematics, the Philosophiae Naturalis Principia Mathematica, typically referred to as simply the Principia. Newton was not alone in this. Historian of mathematics Niccolò Guicciardini writes, quote, "For Newton, as for many of his contemporaries, it was geometry, not algebra, that delivered generality," end quote. In fact, the most influential astronomers of the scientific revolution likewise used Euclidean geometry rather than algebra. Natural philosophy scholar Ed Delian writes, quote, "Nowhere in Newton's and Galileo's theoretical work on motion can one find an algebraic equation," end quote. And he says that Kepler did not use it either. So algebra, the greatest mathematical contribution of the Muslim world, which the Muslim apologist video suggests was the tool on which the discoveries of Copernicus and Newton were founded, was actually not responsible for the scientific innovations of Copernicus, Kepler, Galileo, or Newton. Aside from algebra, there is another Muslim mathematical contribution which is sometimes credited with having inspired Copernicus. Although Copernicus is rightly credited with arriving at the first systematic heliocentric understanding of the solar system, his explanation used a mathematical theorem called a Tusi couple, which was formulated by the 13th century Persian Muslim mathematician and astronomer Nasir al-Din al-Tusi. The Tusi couple was a useful theorem for Copernicus to explain his model, but it wasn't essential to heliocentrism, and it wasn't a discovery which led to heliocentrism. So although the Tusi couple was used by both al-Tusi and the later Muslim astronomer Ibn al-Shatir, both of them held to a geocentric model of the solar system, and neither of them realized how it could be used in a heliocentric model. Nevertheless, it was useful for Copernicus' system. Although there is no direct evidence that Copernicus read al-Tusi's work, the Tusi couple was known in Europe by his time, since it appears in the writings of the 14th century Spanish Jew Abner of Burgos, who definitely borrowed it from al-Tusi, as demonstrated by his use of al-Tusi's notations in his own diagrams. The 14th century bishop Nicholas Oresme of Normandy came to a similar conclusion independently, although his mathematical device differs from the Tusi couple in several ways and uses different notation. Additionally, Dr. Victor Blauweijer of the University of Utrecht in the Netherlands says, quote, "Oresme's description of this matter is very vague and incomplete, as everyone agrees," end quote. The question of whether or not Copernicus was aware of the Tusi couple and the influence of Muslim astronomy on Copernicus more generally is still debated in scholarly circles, demonstrating just how difficult it is to disentangle the multiple intersecting threads of intellectual exchange during the Middle Ages. The fact that Copernicus does not cite any Muslim sources of inspiration is not hard evidence that he did not use them, but the fact that he cites Greek sources of inspiration such as Philolaus the Pythagorean is evidence that he certainly did use them. In the case of the Tusi couple, Copernicus attributes it to the Greeks, citing the 5th century pagan Greek astronomer and philosopher Proclus Lysaeus, who used a very similar mathematical device. However, for the sake of this discussion, let's assume Copernicus did learn of the Tusi couple from al-Tusi's work via Abner of Burgos. If he did, to what extent should al-Tusi receive credit for Copernicus' heliocentric solar system, even though al-Tusi himself never realized that such an application could be made, and remained committed to a geocentric model? Well, that's a matter of opinion, but the actual claim we're testing here is the Muslim apologist claim that Copernicus relied on mathematics obtained from translated Arabic Muslim texts, which were the basis of his discoveries.
Copernicus could have never been able to formulate his model without the book on planetary motion by Ptolemy, or more precisely, the Latin translation of the Muslim astronomer Ibn Shatir's commentary and correction of Ptolemy. Where Tusi uses Aleph, Copernicus uses A. Where Tusi uses Ba, Copernicus uses B, and so on.
It is certain that Copernicus was aware of previous Arabic works on astronomy because he cites several of them. Freely notes that Copernicus, quote, mentions some of the Arabic astronomers whose observations and theories he used in De Revolutionibus, end quote. Freely identifies these astronomers as al-Battani, al-Batruji, al-Zakhali, Ibn Rushd, and Tabat ibn Qura. This seems to support Muslim apologist claims that Copernicus' conclusions were based on the work of previous Muslim scholars. However, out of the 5 astronomers cited by Copernicus, al-Battani was not a Muslim and appears to have been a Sabaean, a pre-Muslim traditional Arab religion. Tabat ibn Qura was definitely a Sabaean, not a Muslim, and al-Batruji's religious affiliation has similarly never been determined precisely, although he was definitely not a Muslim. Regardless, although Copernicus cites them, he does not borrow from their work. In particular, although al-Batruji disagreed with Ptolemy, his alternative astronomical model was even less accurate than Ptolemy's, and was criticized for this by the later Jewish astronomer Levi ben Gersonides. The two remaining astronomers cited by Copernicus are Al-Ghazali and Ibn Rushd. They were Muslims, but both of them had a geocentric model of the solar system which differed significantly from the heliocentric model of Copernicus, and there is no evidence that Copernicus borrowed anything from either of them. It has been suggested that Copernicus may have borrowed from another Muslim astronomer, Ibn al-Shatir, despite not citing him. Freely writes, quote, he does not refer to Ibn al-Shatir, though in his lunar theory he used a model similar to one that his predecessor had developed, end quote. However, Professor Nidal Gueson, who is a Sunni Muslim, an astrophysicist and scholar of Islamic science at the American University of Sharjah in the United Arab Emirates, states, quote, there is no evidence that Copernicus read Ibn al-Shatir and chose never to mention him, end quote. He adds that since Copernicus repeatedly acknowledges other Muslim astronomers whose work he examined, such as al-Battani and al-Batruji, it would be extraordinary if he failed to mention al-Shatir after using his model. Additionally, Gueson explains that although Copernicus did, quote, construct a model that was, in its technical geometric aspects, very similar to that of Ibn al-Shatir, end quote, this model of Copernicus was, quote, later shown by Kepler to be utterly wrong and replaced by a model of simple elliptical orbits with the Sun at one of the foci, end quote. So the part of Copernicus' work which was the closest to al-Shatir's model was not only completely wrong, but was promptly discarded by Copernicus' contemporaries. Thus, al-Shatir's work made no contribution to Copernicus' revolutionary discoveries. It is clear that the only specifically claimed influence of Muslim texts on Copernicus, the Tusi couple, was not at all the basis of Copernicus' discoveries. Even if he did borrow it from a translated Muslim text or obtained it second or third hand via a chain of transmission from other European commentators, the Tusi couple was not the basis of any of Copernicus' discoveries. Instead, it was a mathematical theorem which he used to explain the discoveries which he had already made. Freely says, quote, there is no definite evidence that Copernicus knew of Al-Tusi's theory, which was apparently known to some of his contemporaries, end quote. Gueson notes that while there were similarities between the models of Copernicus and al-Shatir, there were two fundamental differences. Firstly, Gueson notes, quote, Copernicus adopted a heliocentric model, while Ibn al-Shatir and all Muslim astronomers assumed a geocentric model as strictly as possible, end quote. Secondly, Gueson says, quote, Copernicus followed a clear inductive method, while Ibn al-Shatir remained within the Zij astronomical tables tradition, end quote. Commenting on Copernicus' use of work by earlier Arabic astronomers, Victor Bloch observes that Copernicus never used their models to support his own, even though he cites Greek works which substantiated his conclusions. Bloch says that Copernicus, quote, goes out of his way to cite even obscure Greek sources that can be construed as lending credibility to his theory, yet he cites Arabic sources only for observational data, end quote. George Saliba, professor of Arabic and Islamic science at Columbia University, notes that there is very little evidence for any Arabic astronomers contributing to Copernicus' work. After writing that the only three possible sources of influence were the Muslim astronomers Urki, Tusi, and al-Shatir, he observes that, quote, none of those Arabic sources could account for all these similarities, end quote. Urki's work does not contain the theories of Tusi or al-Shatir, Tusi's work does not contain the work of Urki or al-Shatir, and al-Shatir's work did not contain the work of Tusi. Saliba therefore dismisses the idea that Copernicus knew of the works of Urki, Tusi, and al-Shatir, explaining that, quote, it becomes almost impossible to conclude that he knew of all of these works individually and that he synthesized them himself when he did not know any Arabic, nor having had any of them available to him in Latin, end quote. Saliba suggests that an acquaintance of Copernicus may have had access to, quote, some type of an astronomical work that contained commentaries on earlier works, end quote, but adds, quote, no one knows of such a commentary and the problem is yet to be solved, end quote. There is therefore no evidence at all that Copernicus depended on Arabic astronomers for either his astronomical model or the mathematical equations and theorems he used to devise it. The strongest evidence against Copernicus' dependence on Arabic astronomy is the fact that his model was totally incompatible with theirs. As Gueson and Bloch noted, the Arabic astronomers not only never discovered the heliocentric organization of the solar system, they did their utmost to interpret the solar system as geocentrically as possible, and every new discovery they made was retrofitted into that geocentric model, no matter how difficult it became. Even the greatest Muslim astronomers of the 13th century at the Marageh Observatory in Persia never came close to a heliocentric model. In fact, throughout the Islamic Golden Age, Muslim astronomers not only actively resisted any alternative to geocentrism, they also consistently rejected the idea that the Earth revolved on its axis. Consequently, Owen Gingerich, professor of astronomy and the history of science at Harvard University, concludes that, quote, the Islamic astronomers would probably have been astonished and even horrified by the revolution started by Copernicus, end quote. Let's look once more at the Muslim apologist claim with which this video started.
But what they failed to recognize was that most of these manuscripts were translated from Arabic from the works of prominent Arab Muslim thinkers. This paved the way for European development and the creation of new scientific fields such as chemistry and algebra, with calculations that were the basis of Copernicus and Newton's discoveries.
It has now been demonstrated that despite their invention of algebra and their development of alchemy, Latin translations of manuscripts originally written by prominent Arab Muslim thinkers did not pave the way for the creation of chemistry or contribute calculations that were the basis of Copernicus and Newton's discoveries. It has also been demonstrated that the scientific contributions of Ibn Rushd were minimal and that Ibn Rushd himself did not lay the foundation of the European Enlightenment.